Okay, calculus. Chapter 14 is mostly multi-integrals. We call these iterated integrals. And that's where if we have multivariable, we integrate with respect to a certain variable, and that variable is determined by either the dx or the dy. Tells you which variable to integrate with respect to. Now, when you're plugging in bounds for that equation, if you're integrating with respect to y, your functions that are bounds can either be constants or they should be something in terms of x. You don't want to be plugging in something in terms of y to y. That wouldn't really make sense. So usually they transfer over to some different variable. Because if we plugged in y again, particularly and we have multivariables, it becomes a little more complicated to integrate and plug into. So let's just look at how this works for a second. Evaluate the following: the integral from 1 to x of 2xy plus 3y squared dy. This means we're integrating with respect to y, which means this becomes xy squared plus y cubed, evaluated from 1 to x. Now we simply plug in x and we plug in 1. So we have x times x squared plus x cubed minus x plus 1. So that means that's 2x cubed minus x plus 1. Now there's not an extra integral to integrate to, but let's see how this usually works when we have multiple integrals going on. Now we have the integral, the same integral, but then we have an extra step, the integral from 1 to 2 dx after that. So do the inside first. It's the same thing we just got there. We know that this is the answer here, 2x cubed minus x plus 1 dx. Now we're integrating this with respect to x. So this becomes 1/2 x to the 4th minus 1/2 x squared. Oh, this is minus 1. And then this should be minus 1, so this is minus x, evaluated from 1 to 2. Now when I plug in, 2, 4, 8, so we have 1/2 times 2 to the 4th minus 1/2 times 2 squared minus 2 minus, and then everything in terms of 1, so that's 1/2 minus 1/2 minus 1. That's 8 minus 2 minus 2 minus 1/2 plus 1/2 plus 1. That'd be 4. These cancel, plus 1. That's 5. So example B is what we call an iterated integral. Normally we would write them without brackets, but it's helpful to see how these work when you section them off. You always go inside out. The inside limits of integration can be a variable with respect to the outside variable of integration. However, the outside limits of integration should be a constant with respect to both variables because you've done both integrals. So we talked about how here, yeah, I can integrate something with y with respect to x if haven't done x yet, but the outside should be a constant so we can get an actual value. So let's just talk about the outside limits indicated that x was between 1 and 2, and the inside limits indicated that y was between 1 and x. Together, these technically kind of make a diagonal region in R, because all of these we could have reshaped to be single variable integrals with clever substitution. So consider the plane R bounded by f for x between a and b, and between g1 of x and g2 of x for y. The areas are using the fundamental theorem of calculus. Usually we do g2 minus g1 integrated from a to b. So the bounds of integration were from x, and we used the functions to subtract them. Specifically consider x to be the fixed and let y vary from g1 to g2. You can write it. The integral from g1 to g2 dy equals y, and then integrate again with respect to x. So combining these two, you can write the area as an iterated integral. Same one that you would have done in just a single variable in the past. Now, generally, placing a rectangle in the region helps determine the order and the limits of integration. Usually, if you have like a vertical difference between two functions, you want to do y first and then x. Similarly, if it's horizontal, you kind of want to do x first and then y. So if you can draw the picture, sometimes it helps you figure out how you want to integrate. So it says use an iterated integral to represent the area of the following rectangle in two ways. We have bounds a to b down there, bounds d to c up here. It's a rectangle, so we can go either way. We can just do it one way if we want. If we do y first, y's bounds are c to d, then x second. X's bounds are a to b. So what happens here, I mean, we know the area of a rectangle, that's not difficult, but we integrate with respect to y. We get y evaluated from c to d, which is d minus c. Now, if we integrate that with respect to x, that becomes dx minus cx, really, or d minus c, because they're constants x, evaluated from a to b. So it would be d minus c times b minus a, which does represent the area of this rectangle. We know that's the case. We could also do this backwards and get the same answer. If we did dx dy, we just need to make sure the bounds flip respectively if we do it that way. So let's see how we can convince ourselves what something looks like. Sketch the region bounded by 0 to 2 and y squared to 4 dx dy, and then find another representation that gives the same area. Okay, so first we integrate with respect to x. So that's the integral from 0 to 2 of x evaluated from y squared to 4 dy, which is the integral from 0 to 2 of 4 minus y squared dy. Now this is the function that we're talking about. Now if we talk about what's happening here, it says that y squared is less than or equal to x is less than or equal to 4, and 0 is less than or equal to y is less than or equal to 2. Now given this relationship, we know that x is less than 4, if we just draw the picture, and y is less than 2, we can kind of draw what this looks like using bounds. Just draw x equals 4 and y equals 2, and then we have this relationship 4 minus y squared. That tells you that the function should look roughly like y squared, or negative y squared, and this x equals negative y squared, but starting at 4. Now we know y only goes from 0 to 2. We know x has to go essentially from 0 to 4, so it should look roughly something like this, shape-wise. But anyway, if we continue integrating from 0 to 2 with respect to y, this should become 4y minus 1/3 y cubed, evaluated from 0 to 2, which should be 4 times 2 minus 1/3 times 2 cubed, or 8 minus 8/3, which is 16/3. And we'll do more in the next video.